Yeah, so I would like to thank Vukosi for the opportunity to present on the transformer. A little bit about me. I'm Salomon KABONGO. I'm from DRC, Congo, the big one, because there are two Congo actually. And I attended South Africa last year in Cape Town. So I graduated from the University of Western Cape. And I'm currently at in Ghana doing the African Master of Machine Intelligence. Yeah, so I'm working with Vukosi for my research project. And so today I will be talking about transformers, and I'll just start with some a quick overview of sequence-to-sequence model, and after that, we discuss a little bit of the architecture of those models and the limitation that they have and that they are facing. And after that, I will start from the recurrent neural network, the formulation, and explain a little bit the connection from there to LSDM and GRU. And after that, connect the equation up to the attention formulation. And after that, I will now go into the main subject, which is the transformer. I will basically be overviewing the vanilla transformer, which is the transformer presented in the paper, Attention is all you need. So we start by there and go a little bit into the detail of the encoder and the decoder, and after that I will conclude. Yeah, so let's go into the introduction. So first, recurrent neural network, which has been made for dealing with sequential data. So as you know, for neural network, we have the feed-forward neural network and we have recurrent neural network. The main difference is that in this case, we want to account for data that have kind of a certain pattern. There is sequence in the data. For example, let's say if you are trying to process speech recognition or you're trying to get translation, so your sentence has a certain sequential behavior. So that's why people have been using recurrent neural network to model this kind of behavior in the data. So this is the simple recurrent neural network, and here you can see that we have just, I put some annotation there. I don't have very good handwriting, but anyway, I just wanted to put it for dimension. Sometimes it's useful to have that in mind. So here the idea is that we have an input xt. Let's say I want to process the information I like NLP. So at times 1, I have I, which is my current input, and I'm having a W, which is a matrix, a parameter of my model. At this point, I would like my model, you can look at this data here in the middle as your model actually. So you get your input, you multiply it by a certain matrix. And the advantage here with the recurrent neural network is this cycle, because when we are doing the multiplication of our input with the weight matrix, we are also taking into account the past information that was in the sequence. For the example of I like NLP, you will find out that in the beginning we have nothing. Usually we put a beginning of sentence token. You can put it just a symbol to let your model know that you are starting a sentence. So at this step, you can see that st-1 will be here, the beginning of the sentence. So the matrix WSS, which is that parameter that will handle the past information, how to concatenate it with the current information. So the vanilla RNN is just taking the input at times 1, which is I, plus the value of the beginning of the sentence token multiplied by another parameters, and it putting it into a touch function, activation function, and it continues to the next time frame. In this case, for our sentence, it will now go to like. So you can see now that the information in st-1 will have the information that the network has learned from the beginning of the sentence and I. So it will concatenate it. That will be the representation somehow of the 2 previous unseen words. So you can see that we can continue on and on as long as a sentence can be, we just take it every time we take that sentence, we take the previous one, because at the end, basically, you'll find out that if you can see the last vector here, if we continue on the time, we find out that when you finish processing everything, all the information from the past input will be inside a single vector. And of course, this leads to several other issues that we will review very soon in the slide, that lead to people thinking of much more sophisticated approach, like long short-term memory and gated recurrent unit, GRU, which is kind of a simplification of LSDM. And let's first try to see what happened with LSDM. So basically here, we found out that, okay, instead of just coming up with this idea of just taking the past information, as we saw here, taking the past information straight and adding it with the current information, maybe we should find a clever way of introducing what they call gate. The intuition here is like, okay, if I want to process information on a sentence, maybe there are some part of the past that are not relevant to predict the next word. There are some part of the past that I'm not supposed to carry on my contextualize, my memory cell. So they come up with the idea of introducing 3 gates. So they have the first gate, which they call the forget gate, the input gate, and the output gate. So those gates, you can think of them just like some doors that allow the information to pass if they are relevant to what we want to achieve. So they put it inside a sigmoid function for the simple reason that they want it to be open or closed between 0 and 1. So on the opposite here, we don't just, if you remember at this side, we just have one contextual state, but here we have 2 information that are carried on. A part of the new information that are coming, we have the context, and we have also the memory cell. So the memory cell here, as you can see, the right part of the memory cell look basically as the vanilla RNN, but we are doing the pointwise multiplication with the input gate. So, and this input gate will be learned jointly as we train our network to know exactly from where we are, we get a new information, how much of that information can we let it pass through the input gate. And now, the forget gate will be acting on the CT-1, which is the past, the previous memory cell. So it's also doing the same thing with the forget gate. And at the end of all, if you will get now the HT, it means that the hidden set at that current time will be a dot product, a pointwise product between the output gate and the tanch of the memory cell. The reason we are putting in the tanch is because, think about it, if we keep putting CT, we are adding actually the information between CT-1 and the current information. It will go up and up because there is an additive behavior here. That's why we need to put it in some kind of activation function to keep it between 0 and 1. And as you can see, we have a lot of parameters to take into account here. If you look at the number of W, just keep in mind that those W are different. So the W inside the forget, the input and the output are different Ws. So, and we have here, if you count it, around 8, but we have a bias also that need to be considered inputted here. You can view it as inside WF, but anyway, we have a lot of parameters to take into account in this case. A lot of people have been using LSDM and giving a lot of great result, and people thought of what can we come up with a very slight, let's say a smaller version of LSDM or a more light version, because we want to make it train quickly. We want to make it produce some kind of result that look as good as LSTM, but take less time to compute. So this is the idea of GRU. So instead of having those 3 gates, we just come up with a single gate. So now the idea is just using this clever idea of having 1 gate that just the same behavior that I explained in LSTM, but here we just take the count information, we do the product with the output from the gate if that information is important to be carried on in the next time step. If not, we are using 1 minus GT, which will only consider the information from the past. So the intuition here is as follows. If you have like, let's say our example was I like NLP, at like, for example. So this is the information that I have here in the new information. I hope you can see my cursor. Yeah. So you have like, for example. So remember that we have the beginning of the sentence and I that have been processed inside ST. Let's hope that everything was taken. So let's say that, for example, you found out for your task that like is not important to be carried on ST. So you basically it's an input, but you decide to forget about it. So what will happen here, GT here will give a signal such that that signal will make that this part of the equation will go to 0. If this goes to 0, you'll find out that this equation will make this 1 to 1. So basically, the current time step will be exactly the same as the previous current state. So it has been shown that it actually giving results similar to LSDM, but with less computational requirement. So now, now that we have an idea of what is RNN, LSDM, and GRU, I would like now to discuss the architecture of the sequence-to-sequence model. So the sequence-to-sequence model was born in the field of language modeling. Language modeling is when we are trying to model language. We want to predict the next word, giving the previous word. And the idea here is to transform an input of sequence, as the example I give, I like. You can just try to say I like, and what is the most probable word after I like. It can be I like eating, I like sport, whatever. So language model is how can you model this kind of behavior. So we want to transform an input sequence source to a new one, the target, and both sequence can be of arbitrary length. So even in the context of speech-to-speech translation or machine translation, your encoder or the first part, the sequence that is coming can be a sentence in French, for example, and the other sequence on the other side can be the same sentence but in English. So you can see that the sentences are sequences, so we can use the sequence-to-sequence model in order to train a model that will be able to translate, to do machine translation. So what is the encoder in this case? So the encoder takes the sequence and compresses the information into a context vector, as explained earlier. So you take every sequence every time you decide what is important until you reach the end of the sentence token. At this step, you have basically all the information that you could get from your input sequence. And the decoder now, the point is that given that vector, fixed vector length, how can you use it to do translation or to do whatever you want to do, language model? So the point now is how can we use the context vector to emit and to produce a certain output. So from what I explained earlier, people have been using LSDM, bidirectional LSDM or bidirectional GRU to kind of get the context of a word, put everything, get the last vector representation that contain all the information of the sentence and pass it to another recurrent neural network that will be able to make prediction at a time. And this has been working fine, but there are some limitation actually with what has been used in the past. When I mean limitation here, it's not directly linked to the architecture of sequence-to-sequence, but the underhood where they are using LSTM and GRU, those are actually the limitation of the behavior of the sequence-to-sequence model when we use GRU or LSTM. So now the issue is that normally the last representation of the input is supposed to be a good summary of the meaning of the whole sentence. So if I'm inputting something like, I like NLP, so the last representation should carry all the information that is inside the sentence. But let's say if that sentence is very long, let's say it's a paragraph or it's all the book, you take a book, you split it and you put all the information on all the text in the book inside a recurrent neural network or an LSTM. So you are supposed at the the end, your last state should contain a vector, a fixed size vector. That's why I put fixed size length vector in bracket. Very important to keep that in mind. That fixed size is supposed to contain a summary of all the book. This is not always what happened in practice, because we found out that the network is kind of forgetting some long-term dependency. Like if the book was 500 pages, you find out that the summary can help you kind of do well for some pages, but some pages that are very far from the last are not really captured in the fixed length context vector. So this is a design problem, and the incapacity to remember long-term sequencing has been motivating a lot of researchers to think of what can be a better way to deal with this kind of scenario, as to improve the accuracy of our translators, or to build better language model. So now people come up with the intuition of attention. So before I go into the formulas, I'll just try to talk a little bit about the idea of attention. So now, instead of, let's say, putting all the information in a single fixed size vector, we are thinking of just using LSDM or GRU. You can put them together to just get the word representation or the embedding of every single word. So like the vector representation of every single word as you go through times. So it means that if you, for example, use the bidirectional LSDM, you go for one direction, like NLP, you get the vector of I, the vector of like, the vector of NLP. And the other way you turn your LSTM, you start from NLP, like, and I. So actually the vector representation of like will be the concatenation of the representation in one way and the other way. So now instead of packing all those information in the last vector, we just keep it that way and concatenating, and we put a certain mechanism on top that will actually weight how important each representation can be for the following task in the decoder or what you want to achieve. So now that is the idea. How can we weight the importance of information that is inside the encoding? Let's say if I start telling you a story, I start reading to you a paragraph, even a human, you cannot start memorizing every single word that I was reading in the paragraph. You will, in your mind, get information that are important for you to get the clear picture of what the paragraph is about. But what has been used in the past LSTM and GRU, we're trying to get every single information on everything that is in the paragraph. So that kind of the high-level intuition of that motivated people to come up with the attention. Now let's look a little bit into the math that motivated those formulations. Yeah, so here we have the naive transaction function. I know you remember just here I had this bias. In the other formula we didn't have this B. Yeah, it doesn't matter, so you can just ignore that. So basically here at time step t, for example, if we have gone far, like at time step t plus n, we are trying now, you know, all the person when training a neural network, there is this thing of backpropagation. And when we are trying to backpropagate the error 2 times, you find out that we will be basically multiplying UT several times as we go back through time. So that was the first big issue with the vanilla RNN, the simple RNN, because here at times HT, as you can see here, let's say time H1, if we are modeling something that a paragraph of a book that can contain thousands of words. So if I want to propagate the error from word 1000 and to the first, maybe the second word, you find out that I need to multiply this matrix U several times. U is actually the matrix that multiply the state T minus 1. So I need to do it several times, and this leads to a problem. What is the problem here? Because you're multiplying the matrix several times. If the matrix, the value of the eigenvector of the matrix are very small, you find out that you are multiplying small value because that the composition, if you put power, it actually just the power of the values, and you find out that if they are very small, you will have exploding and vanishing gradient that can appear directly from that formulation. And now people start thinking first, when they thought of introducing LSTM, the intuition is, how can we skip connection? Let's say when I want to get the error at this step, I don't consider all this step, I can kind of jam within my propagation. So when I want to get this error here, sometime I can consider this, but sometimes also I'm considering directly the error from here, HT and HT plus N. So the idea here, as you can see from the equation, this equation actually is modeling this intuition. And one of the things that I really find useful when I'm learning this stuff, personally, when I get the intuition that motivated the mathematical formula, it becomes intuitively for me to even reproduce it or write it down than just looking at the formula. So like the intuition of skipping connection has been what motivated this formulation to allow the backpropagation step to not just multiplying you several times, but sometimes skipping the connection to avoid vanishing gradient and exploding gradient. So that the additive update that was introduced by LSTM and GRU. So from here, how can we move to the attention formulation? So the last formula is giving us that formula of the LSTM and GRU update. So this is what I'm reproducing at this step. So the idea now, if we want to model those adaptive shortcuts, and if we enroll the formulation of HT for all the time step. Let's say if you look at this first formula, it's just that RNN formula, but here we are applying the same formula like recursively on HT minus 1. So this is UT minus 1, H2 minus 2, and the same thing. And we can keep doing the same thing now on H2 minus 2, T minus 2, and so on and so on. So you can see now that we can write the candidate update, which is the HI, as a weighted combination of previous input or previous hidden vector. So like now what is going on, we are trying to achieve the intuition that I explained earlier. We want to get a weighted average, or give weight to our context vectors instead of just concatenating them in one vector. So this what we can do first to get into getting that kind of behavior that we want to model. So you can say that the sum is for the weighting, and the combination is all those products of use that you can see by continuing this development. So now we need to do some kind of tricks, mathematical tricks, to be able to go straight to the attention formulation. So at this step now, we are trying to free the dependency on weight. So we're trying to free the dependency on those two products. So we are introducing a WI, which can be seen as the attention of HI and the current input. So the formulation of the attention, there are many formulations. I will show one later on. So actually, we are trying just to change to make this one independent, to free that dependence that it has on the formulation that we had previously. So we're introducing this WI, which is exactly the attention between HI and XT, which is the current input. So here we are just replacing HI by F of XI, and now we want to introduce the matrices. We introduce three matrices. If you have been looking at the attention, you will you have been comforted and seeing this V, key, and Q. So the intuition here, we have a key, the query, and the value. So the query basically here is a matrix that is multiplied by the embedding of the current word, and we have another matrix key. So all the three are actually matrices, and what the attention basically is doing is just matrix product. You can look into that online. I will not get into detail on that. And this basically gives us what is known as the self attention or single head attention. And from that, you can see that with the single attention now, we have something on top that is attending on all the vector in our context. Now we are trying to find out if we can introduce several mechanisms like that. In the paper, attention is all you need. They used 8 attention. I will explain later on why it's important to use more head of attention. But they use 8 attention, and the intuition is like you just use the same formulation, but with different matrices, different view, different skew, and different scale. You put them together, you concatenate them to get what is called as the Milky head attention. And at the current formulation, you will see that there is no account for position. So the attention as we define it here are position invariant. So for example, if you look at the attention of ABC, let's go back to the example I was explaining earlier. The attention of I like NLP will not be different from the attention representation of NLP like I, which kind of not making sense in the context of translation or any other context of NLP task or any other computer vision implementation. You need to find a way to make attention understand the position behavior, to know what is supposed, what came before others, even though it's weighting the position, but how can we make it able to know exactly what was the position of the word that they are focusing or attending to. So that that's what we are adding here as PI. So we are adding a certain vector of the same size as the input, because you will see later on that we need to add it to the embedding of the word, the current word. So what we are doing, like for every word, we are taking that embedding, which is the f of xi, is the embedding of the xi at times 1, for example, x1, plus the positional encoding, as it's called, of that word as well. So where do we get those PI? And you can see that we are adding it not only on the value part, but we are adding it on the query and the key. So basically, if we go back here, you'll find out that we don't just have this formulation over here. We have the key of f of xi plus the positional encoding. The same thing is done also for the query, and the same thing also is done for the value. So this is what this formulation is about. So where are we getting those positional embedding from of positional encoding? So there is a link that I put. You can read more about it. You can use the learning positional embeddings. So you are learning it gently when you're training your network, or you can use the sinusoidal positional embeddings. The reference are those paper of Vaswani and others in 2017. You can have a look at it to just understand how they initialize those, they use those embeddings, but mostly they are value between 0 and 1. Yeah, that used to kind of give the position of your to your attention. So finally, now let's discuss some detail now about transformers. The difference with all the other implementation, I talk of LSTM, GRU, and all those stuff, is when you use a sequence-to-sequence model, basically we have been just using them, and now what made the transformers popular is because they don't use at all any recurrent neural network or LSTM inside. They are built only on top of attention. So it's like you just put attention on top of attention. You just put block. I will show you a picture very soon. And they all model. So it's still sequence-to-sequence architecture, but now the encoder and the decoder is made only of self-attention, which is in this specific case a multi-head attention, has to be able to model long-term dependencies. So as I say, it's following the sequence-to-sequence architecture, but it all stack of self-attentions. Not only that, but we'll have a fully connected layer for both the encoder and the decoder. So just a little bit of refresher of sequence to sequence, just to make sure that we are on the same line before going further. So at this level, we encode an input, a sentence like an NP, for example, and that sentence can be this token of that word I like NLP. You can take it, in this case, we have X1, X2, and X3. That's the sequence. We want to change it into the sequence of continuous representation. And then we will have now Z1, Z2, and Z3, which is actually a representation of those two words, but in a continuous space. And now what we are going to do is, given that Z, the decoder now will be able to generate the output at a time. This is very important, one element at a time. This is the autoregressive behavior. So let's say, for example, you want to translate I like NLP. So when you put all the Z1, the continuous representation, Z1, Z2, and Z3, you pass it to the decoder. The decoder will start with an empty token, end of sentence token. It will go to the translation, and it will produce, if we translate in French, it will say je. I know French as well, as I say. So je, and after that, it will now take beginning of the sentence and je, feed it again to inattention and do everything, and produce the most likelihood that can come as a translation after je. So for our case, I like, j'aime, aimer. So now it will put beginning of the sentence je and aimer as the next input, and so and on. It will after a while predict the end of sentence token, and you have the translation in the language that you are trying to model translation systems. So this is how the encoder and the decoder work jointly. But let's look a little bit deeper on the transformer itself. The first proposed transformer architecture, which was come up in this paper, attention is all you need. So basically, we have an encoder part, which is this part on the left, and we have also a decoder part, which is the part on the right. Will in the next remaining few slides, I think two or three slides remaining, just go through the detail within this network. So basically, I'll just start from this picture. Maybe I will be repeating myself next, but I would like just to comment a little bit on this picture first. So here on the input side, we get the input embedding. So at this one, you can either use a Python with embeddings, or you can train your own embedding. So when you have a word, you get the embedding of that word. So what is going on here? You are adding that embedding with the positional upcoding, that PI that I explained later on the slide. That's why I was saying that it has to have the same dimension so that the addition can be possible. And after that, you can see that this connection jumping the Milky head attention. This is due to the residual connection, and I think I will talk about it on the next slide. But here, when you get into the Milky head attention, the Milky head attention actually is attending in all the representation from your input to decide which one to carry on and to give to the decoder as to achieve the task that you want to achieve. And after that, we are passing it to a 3-4-1 network to get the nonlinearity also, had some assembling, putting model together. And after that, we are using layer normalization just to help the training process and stabilize, making the training stable. And the result from the encoding encoder part. So this is just an illustration, but in this case, we have 6 modules like this repeated on top of each other. So just for visualization purpose, but we have those NX on top of each other 6 times before it goes into the decoder part. So the decoder part is kind of doing the same thing. We have the embedding of the decoding. So actually, in this case, we have 2 vocabularies. We have a vocabulary, in the case of machine translation at least, we have a vocabulary for the English and the other vocabulary for Xhosa or for French or Lingala. You have those vocabularies. So From there, you can get the embedding from one language, the embedding for the other language, use positional encoding respectively. And here you use, the structure is kind of the same. I will go deeper on it. I'll use multi-head attention again, use layer normalization, you skip connection as well. You use another multi-head attention that will attend from the output of the encoder and the input from this part, which is the decoder, the information from the decoder. And we pass it to a feed-forward network, we pass it to a linear transformation, and we get the softmax. Why the linear transformation? Because we have a dimension that will come out from the feed-forward network. We want it to be equal to the size of the vocabulary of your translated language. If you want to translate in Lingala, for example, you need that the vocabulary of the Lingala must be you know, the way we use in PyTorch, for example, RNN.linear from the output of the decoder to the length of the vocabulary. The reason that we want to use softmax on all the vocabulary to decide what is the translation in that language that is more probabilistic, that is probable to be predicted given the encoder representation. So that the detail, but inside the mid-head attention, we have this calculation of those matrices, value key query. We'll talk about it, I think, in the next slide. So let's now look. How many minutes do I still have? I'm not quite sure. I think.
How many more slides do you have?
I think I just remain with 2 slides. I think.
Yeah, that's fine. Yeah.
Okay, cool. So let's look a little bit on into the encoder. So as I say in the picture there, you just see 1 blocks, but in reality we have 2 blocks. We have 6 blocks. This I'm just explaining the attention is all unit paper. So they have 6 identical blocks. What are those blocks made of? So each block has 2 sublayers. So we have first a multi-head self-attention and a simple point-wise fully connected feed-forward network. Why multi-head self-attention? Because as I said, that I will talk about it later on, when you have a simple head attention, you are only getting some kind of representation that the self-attention can capture. If, for example, you have a sentence like Salomon is speaking peace from Annie. So when you use attention on this sentence, the attention can relate E with Solomon because it's co-referring Solomon inside the sentence. But that's not the only connection that he can be referring to. So if you use many head attention, it may be able to capture some of the dependence and the connection between the words. Up to now, people are still not able to explain exactly what the multi-head attention is getting represented as a representation in detail. So basically, we have a multi-head attention and a fully connected feed-forward network, and each of those sublayer is preceded by a residual connection. So the residual connection, the point is, as I explained earlier, we want to skip those connections in the LSDM intuition. So we want to skip, to model this behavior of skipping the information. Let some information go to the multi-head attention, but some information are skipping and added with the information from the multi-head attention to kind of produce better result and avoid some of the issue that can come up with not doing that. So, and after that, we use layer normalization just after the point where the multi-head attention, and this is repeated for all the 6 blocks. So this is basically what the encoder of the attention is made of. Now, what is the decoder? I think this is kind of my last slide. So the decoder now is made of the same six identical layers, but there is a little bit a difference here, and I would like to comment a little bit on this quickly. So what is going on here is when you use the multi-head attention on the decoder, you want to make sure that you are not giving your multi-head attention all the information of of your input in the decoder side. Why? Because let's say you are translating something from English to French. I like NLP, which is Gen Natural Language Processing. I don't know the NLP in French, how they call it anyway. So if you give it all that sentence as to the input of your decoder, it may memorize and just give it to you as a translation. So what happened, the idea here is to add some kind of masking to mask some part of your input of the decoder so that your network can learn how to predict them. Let me explain. I like NLP, so I concatenate everything. I have the representation of those zip, and now I give an empty token because I have nothing currently to the decoder. To the decoder, the empty token will query the information from the encoder, and from there it will do matrix multiplication and a lot of stuff going on under the hood, and it will predict what is the most probabilistic word that can be predicted giving the beginning of the sentence token and as a translation to the representation of my encoder. And then it will be je. And after that, it will take the beginning of the sentence and je as an input to the decoder on the next time frame. It will do so until the softmax will, because as you may know, the softmax is just producing it is sorting a probability distribution because it's making all the value summing to 1, which is the criteria for something to the probability distribution, and all the value are greater than 0. And now, until we predicted the end of sentence token, that will be the translation of your language. So that's why we are using a modified Milky head self-attention. They are not the same. This is very important. This Milky head attention and here are masked Milky head attention. They have the same functionality, but they don't receive the same input at every time frame. Okay, let's round up, and we have the same thing, fully connected feed-forward network, and we have a Milky head attention. This is something that we are adding on top of that because we had 2 sublayers on the encoder part, but on the decoder part we have 3 sublayers. So we have the modified Milky head self-attention mechanism, we have a feed-forward neural network, and we have also a Milky head attention that is attending on the output of the encoder as well as the input that is coming from the process input from the decoder part. So that's basically what the decoder is made of. Of course, we have the residual connection as well as the layer normalization that follows. So in conclusion, as we have seen, the vanilla transformers is totally made of attention, and this has been a revolution in the NLP community. People have now been using transformers inside BEG to construct some models that beat a lot of baseline and produce amazing results. And this was made possible by the power that the transformers brought to the community, and that ability to be able to deal with the issue that LSDM and GRU were not able to solve at that time. So there have been several work to just making it train faster or to allow the long-term attention span. I put some references there that you can see at the end of the slides. And so those are the improvements that have been made to make the transformers quick to train and able to achieve better results than the vanilla transformer. So those are some of the references. If you're interested, you can look at it for more detail. I would strongly advise this poster by Huang, 2020, just published it like, I think, last week or so, about the family, the transformer family, discussed a lot of transformers that came as a continuation of the vanilla transformers, a lot of detail that I was not able to fit in these presentations, and there are some other resources that you can look at is to get some more insight on what the transformers are. So that will be all. Thank you very much for your attention.
Okay, thanks so much about for this presentation. It's like one of those things where for the last year or so, you see all the work, you understand somehow how some of these things kind of work, and then you use them. But this actually goes into, especially on the transformer side, and then also thanks from going all the way from RNNs through GRUs, LSTMs, through attention, and then to the transformers. So are there any questions from the rest of the group? Sorry.
I have a question.
Yep, go ahead.
So Solomon,
Yeah.
we know that mostly transformers are used in machine translation, right? So we know that the assumption is that you have text A that is corresponding to text B in a different language. So how would the decoder of the attention visual unit architecture change if you then want to apply the transformer on a classification problem? Like, what would be the input to the decoder then?
Okay. Yeah. So actually, if I get you right, you want to use the same idea, but to do classification.
Yes.
Okay. Yeah. So basically, I was actually having fun playing around with that. On my research project in South Africa last year, I worked on the Internet Movie Database. I don't know if you know it. It's just a review from people giving some kind of the feeling about a movie, and it's a classification task. We want to say if it was a positive review or negative. So what I did past there is just using word embeddings and using normal classification. But to answer your question, what's going on is that people have been using BERT. BERT is a language model, but it's built on top of transformers. So what's going on is like when you use the input, your encoder basically is processing all your input information. So they use a certain token that they call CLS. You can call it like the beginning of the class. That will be a token that you put together with your input. In the case of the review center, you can put it as the input, and at the same place on at the end, like the output of the encoder, you will just, if you are using PyTorch, just put in top a classifier that will take the representation of the hidden, like the representation from the encoder, and map it to, if you are doing binary classification, just do NN.linear from that dimension, it may be 1,000 or million, I don't know, to 2 that will, to 1 or 2 that will predict, do binary classification, you put a cross entropy there and you train your model. So that's what you can do. And what is amazing is that without just using the pre-trained BERT, people have used the same things and put a classifier on top, and the result has beaten a lot of state-of-the-art that people have been using some other complicated stuff to do classification. Yeah.
Okay, so the way I understand it is you just have your encoder, and then on top of your encoder, you just have your linear head, which will do the classification itself.
Exactly.
Am I getting it right? Okay.
Yeah.
All right, cool. Thank you.
Okay.
Any other questions? Okay, so okay, my question was maybe if you could give us some intuition about the distillation process. So the challenge we're having with these models is we're getting bigger and bigger and bigger and bigger, way more parameters that you need to now learn. So now people are trying to do distillation, and what's actually going on there?
I'm not sure. I didn't look into that. They were discussing about it, but I didn't look deeper into that. I don't know what they are doing exactly.
Okay, no, that is fine. Okay, guys, any more questions?
Solomon, it's not a question, but I don't know if you have. I saw that you recommended some references. Do you perhaps have any online learning material that you can point some of us to?
Yeah, sure. There is, by online, you mean an online courses or something?
Yeah, whether it be blogs or online tutorials.
I will strongly advise going for this link. It's a very long blog post that is very recent, and they kind of explain very cool stuff on transformers and some how actually if you go to after this block, you will see the other block of the same author. You will find out that he did how can you do classification with birds, and you can read it as well. It's very cool.
All right, thank you.
Salomon, after this, can you just respond to the email I sent to everybody? And just attach the PDF
Sure.
of the slide. Yeah.
Okay, sure.
Okay. Last chance for questions. Mpo's first question was going to be my question as well. So actually, thanks, Mpo, for asking that question.
All right, cool.
Yeah. Any other questions, guys? Okay. If not, Salomon, I really want to thank you for taking the time to put this together. And as well as going through that, guys, the slides will be available on there, and then I think this also removes partly some of that. When people are talking about transformers, you'll have some intuition. There's still more deeply if you want to go into that. It is worthwhile to understand how kind of the RNN space has actually evolved over the last few years and what more things are actually going on. And yes, it is useful for sequence to sequence work. And yes, now what happens when you need to do sequence to classification is an interesting thing, because you can also then start thinking about, is some of this actually used for things like time series that might have periodicity inside them, and you want to ignore some parts of the input. So guys, enjoy your weekends. We will all catch up, I guess, next week. And just stay safe and stay healthy.
All right, cheers.
Yeah, see you. Cheers, guys.
Cheers.
Bye-bye.
Cheers. Bye-bye.
Bye.